Hello, myself Bharat from TVS. So today I'm going to discuss about advantages of SCE-MI-based BFMs. So what this SCE-MI stands for? It basically stands for Standard Co-Emulation Modeling Interface. And BFMs, as you all know, it's bus functional models. So we'll just go through this flow. Just give the introduction about what SCE-MI basically is, and the existing problems in the emulation platform, and how exactly the SCE-MI solve this problem, and what exactly co-emulation modeling means, and different types of SCE-MI models, and the example of a SCE-MI model implemented by TVS, that is with Ethernet as example. So what this SCE-MI basically does, it basically provides an interface between the software and hardware. The software part is the test bench that is written in the high-level language like System C, and your hardware is the DUT that is placed on FPGA on the emulation board. So those two are basically connected through SCE-MI infrastructure. So here if you see, so this is basically the software part of it, where you have developed the test bench using System C or C++. And here is your emulator where your DUT sits. And here stands the SCE-MI infrastructure, which basically has two parts, software and hardware. The hardware part of it is called the SCE-MI BFM or the transactor, which is basically a synthesizable model which sits on the FPGA, and it acts as a driver to the actual DUT. So that transactor speaks to software through SCE-MI infrastructure. So what are the existing problems that are faced on emulation platform? You are basically unable to reuse the test bench used for functional verification in the emulation platform. And if you want to make it to reuse the same, it requires a lot of effort because we need to create a separate environment for emulation platform. And also all emulators uses proprietary APIs. So this makes very difficult for software products to port to the different emulators, thus restricting the solutions available to the customers, since they will not be able to port into different emulators once they develop the System C models or software models. And also the existing APIs are at gate level and it's not available at the system level. And also the customers are now reluctant to invest on proprietary APIs because the market value will be less and also the productivity will be less, since they should be working only on proprietary APIs. So how SCE-MI solves this problem? So SCE-MI basically enables to reuse the existing test bench, which is written in System C or high-level language, and helps to use the same for even for emulation platform. This is done basically using SCE-MI DPI or APIs. So we basically use APIs in order to do that one. So I'll just touch upon that later. And also it enables the portability of transactor models between emulation vendors and makes possible for IP developers to write only one model so that the same model can be ported to different emulators. And it enables the system level scenarios just generated at the verification stage to be reused on the emulation platform. And also it enables to develop user-defined APIs and thus helps in more customization. So this is how the co-emulation modeling looks like. So it's basically the process of modeling and simulating a mixture of software models represented with an abstract level, simultaneously executing and intercommunicating through SCE-MI API with hardware models represented with RTL level of abstraction and running on an emulator. So here you can see the software model. There exists a SCE-MI infrastructure which is connected to a SCE-MI BFM, which is synthesizable, and it sits on hardware emulator, and which in turn is connected to the actual DUT. So there are two SCE-MI models available. One is macro based, the other one is function based. So in case of macro based, we need to instantiate macros within the RTL, and then we have to communicate with the test bench, and it does through simple handshake mechanism. So once the DUT is ready to receive the data, the software will just give the data and vice versa. So this is one kind of model. And next is the function-based models. So this is basically, it uses DPI to implement the SCE-MI infrastructure. So here the transactor sits next to DUT, and the test bench will talk to transactor, which in turn talk to DUT. So next, what is the difference between these two models, and which of these models are appropriate to use? So the macro based, the abstraction level is closer to RTL, and whereas the function based is more closer towards transaction level. So since, and also the clock control, in case of macro based, it can be controlled explicitly, so that it can cut the DUT clock, such kind of stuff. And whereas that is implicit in case of function based. And this macro based will have predefined API, and function based will have user defined API. And ease of use, it is just easy to use because you'll have the available macros. You need to just instantiate within the RTL. Whereas the function based, it's more of intuitive. You need to define the function and you need to implement those functions. And also migration, it's easy with Altec SCE-MI Sim, but this function based is easy because most simulators support a DPI. So which model is appropriate? The function based is widely used. This is because if we use a macro based, it has to be instantiated within the RTL, and that cannot basically go into silicon at the end. So the function based is basically used wherein a transactor is built, which is synthesizable, and even after once the chip is done, we can place the transactor and drive it. So that's why we prefer function based model. So here at TVS we have implemented this for Ethernet. So here we have a simple SV test bench and the DUT. So the SV test bench talks to DUT through virtual interface, which is a handle to actual physical interface, which is not suitable for emulation platform. So the connection between the SVTB and the DUT is basically done through C++ linkage, C or C++ linkage. So here if you can see, there is a TB and the DUT. So these two are connected using C linkage. So this is a DPI function where you import the function and export the function, and the DUT does the same. So the implementation of the function is done in C. So here we can clearly see the partition between the emulator side and the simulator side, so that there is no requirement of any additional modification for the existing test bench used for functional verification. The same test bench can also be used since it is clearly partitioned and can be also used during emulation. So this is how the actual environment looks like. So this is the software simulation part, and this is the hardware emulation. So here you can see the SCE-MI interface, which has the hardware side and the software side. The hardware side is the transactor.sv file, which is synthesizable, which is placed on the emulation. And the software side is the C functions basically. And this is the SV functions, which call the C functions to pass the different data item variables which in turn will be taken by the transactor and it will drive the data to DUT. So here we have also built the UVM wrapper in order to get more controllability and also to bring in the methodology. As you all know, the advantage of UVM methodology. So this is how the actual environment looks like. So the process involved is while using the DPI. So these are the corresponding data type mappings that were done. The byte in DPI in SV, it's corresponding to character in C. Similarly, the rest. So these will be done automatically when you use a keywords called context, such other keywords. So this, the user need not worry much about it. So these are the APIs that were used. So this is a configure API where it has all the configuration parameters for Ethernet, like frame gap value, padding, SCS, extract type, and the rest. And next is the get configuration from the transactor that basically returns the current configured value of the Ethernet. And next is the to provide payload, user-defined payload. So again, we have a API for that, send frame with user-defined payload with all the destination address, source address, and all the rest of the packet variables. And this is other callback APIs, where if you want to get the callback data, so we can just use this callback functions as well. So if we come to the simple test case, so what basically does is, whenever we want to transfer a variable or we need to provide data items, we need to just export it. So once we export a function, it receives the variables from the C side, and once the transactor gets those variables, it just passes to the DUT. So here we can see the import function is Ethernet transactor ready. So it will be waiting for the ready. And next, whenever the ready is done, the user has to send the data. So for that, we need to do export. And so on, the import and export functions happens. So whenever you want to transmit data between the C and the SV. So similarly, this is for read DPI functions. We have transactor put data, where RS data received from DUT data is sent to C world. And also the AX Ethernet data received callback, where the function is called once the valid packet is received and sends complete packet information to CPP. So this is about test case. And the similar model can also be done for system C, where here exactly the SCE-MI infrastructure sits, and here it's a VBus transactor as an example. And here is the system C test bench, wherein you can directly pass the variables to the hardware using the SCE-MI interface. This is how the structure looks like.
Right. When you say that you are communicating across DPIs, right? So on one side you are having a C environment, and on the other side you are having an SV environment, right? Right. So this, so when you are generating the stimulus, suppose from the C side you are sending some stimulus, but the C side environment is a static environment, and the SV side environment is not static, so you can do on the fly as well. Then how you maintain that synchronization?
So basically what we do is we create a FIFOs wherein we populate the initial data at the 0 time. So whatever the data packets we have, we just call the C functions and then we pass it to the FIFO. And thereon, the transactor will drive it during runtime dynamically. So at the 0 time, all the data items, say suppose some 100 packets or something. So you need to store those 100 packets on a FIFO at one shot, and then the transactor will pick from the FIFO and it starts driving the data.
But when you are having C checkers, so C has sent the stimulus. So design is responding with some response, right? So how you implement the checking mechanism in C, because C is static in nature.
Yeah. So for checking part of it, we use a callback function. So based on SV events, we just take a callback function and we just check the part.
Is it transaction based? It's all,
Yeah,
all transaction based input and output. They read back the data via transactions as well. Okay. Any more questions?
So this two SCE-MI models you mentioned about, macro-based and function-based. So which one, from performance point of view, which one would you recommend, for instance?
It is.
Good question. That's the one I was going to ask.
So the function-based is preferred because the macro-based, they actually have to instantiate the macro within the RTL. So it's not advisable to do that thing. They are in the box, but they are not in the actual chip. The actual chip is separate, and transactor sits in only in emulation.
From a performance point of view, which one is best? Which one works fastest? Performance point of view. Or didn't you check that?
I mean, the performance side, I mean, I'm not sure about it.
You didn't measure the difference in performance. My guess is that function basis as well.
So from your software side, for instance, when you are passing payload or data, and if that is of variable size, right, that is not fixed size, every packet is variable size, then I guess this, because function based, with every call, fixed length of data would be passed to the hardware side. So that's what my impression, or that's what I heard, that in such scenarios, probably macro-based SCE-MI model might be more efficient.
Okay. So I haven't really tested from the performance side of performance point of view. Yeah.
So for instance, let's say your function, if it is passing 100 bytes per call, and in one call you just have 8 bytes of data. And if you make a call, then still it would pass only 8 bytes or 100 bytes.
Yeah, it will pass all the 100 bytes.
So that means we are kind of wasting.
Yeah, that is true. So probably the performance side of it, I need to just.
Okay. Also, one more question I had. In this environment, for instance, did you measure performance when you ran this environment on simulator and when you ran on emulator? How much performance did you get?
The actual performance on the emulator was personally was not done by me. It was done by our technical team. So probably they can provide you all the details regarding actual performance enhancement that was done on the emulator.
Yeah, because that's here.
Yeah, so our technical team have already done that one. Okay. So on real running on the emulator and looking at the performance, so we'll definitely get back on that.
Yeah, so if we can provide that data. It was done on site with the customers. Okay.
I was also more interested in listening, for instance, what can be the best practices when we are designing our test bench for this kind of environment, acceleration friendly, or which can be accelerated, which can be used for emulation. So what can be the best practice that we should keep in mind when we are designing our test bench? So if you have some inputs, that would also be very nice to hear.
Yeah, so that input can be not right now. so I can get back to you with our technical team.
Thank you. Can you go back to this previous slides where you shown this UVM wrapper?
Yeah.
So I was interested to know what does this UVM wrapper? You have an agent there. What is the need of wrapper? I was more interested to know about that. What is that?
In the UVM wrapper, in the sense we have the initially we developed just simple SVTP in the system Verilog. Then we just migrated to UVM. I mean, we changed the environment from system Verilog to UVM. So what we have basically done is to generalize this part. This can be SV or this can be system C.
Okay.
So in order to distinguish that one, we have just made a separate part of it so that this can be called as UVM wrapper in this structure.
You mean to say that inside is not necessary to be an SV, it can be a C based or?
True. Okay. Very true. It can also be system C.
Okay.
So that's what I have shown in the last slide actually.
Okay. Yeah, thank you. Thank you.
Hey, so in this, at what clock speed does the hardware emulator run? Any megahertz or?
Sorry?
Like at what clock speed does the hardware run?
No, that I need to pick up on that.
Okay. What kind of?
Okay. Because I haven't worked with the emulation platform as such. So because we'll be doing at the customer side. So basically our technical team can get back to your answer. Because the most part what I was part was to include this side of it. And even this was done on a simulation basis, simulation platform. It was not on an emulation platform because we do that one only on the customer side. So that we can get back to that answer, my technical team actually. So,
what kind of designs has this SCE-MI being implemented and used in the field?
No, it can be used for any design, right?
Yeah. So I'm asking for like few examples, just to get an idea of what kind of designs are being tested using this scheme.
Yeah, you can use it for, as we have used for Ethernet, we can use for SPI, SPI, any other serial protocols, USB. For many protocols, you can use it.
No, I mean, what kind of DUTs have been tested?
Yeah, that's what I'm talking about. This DUT can be an Ethernet. I mean, the slave of it.
Okay. So basically peripherals.
Yeah, peripherals. Basically peripherals.
So you take one peripheral at a time and then verify it.
Yeah, exactly.
And then set it up for the next one.
Yeah. For that, we need different transactor. Because this transactor cannot be generalized. It is the interface specific. So if you move to a different interface, you need to build a different transactor.
A lot of people use emulation for SOC verification. And as Surinder mentioned, you often do it for performance as well. So you put the whole chip on there, you put the software on top of the chip. But this then allows you to drive traffic in from X. So for example, if it was an Ethernet SOC, you could be driving Ethernet packets into the SOC through the emulator using the software simulation.
Design size is large, right? Then you can't really put the whole thing in the emulator and also have a UVM test bench, which
you can. The emulator can, depends on your emulation provider. But sometimes have to go to, depends on the capacity of the emulator.
Also the thing is like your UVM test benches, right? They don't really scale up to system level normally, right? Like you have a multiple, like you can't test this for the whole chip with just one interface, right?
I've worked with UVM environments where UVM is for the whole chip, yeah.
Like for example, like you won't have one interface, like you might have PCIe on one end and then you might have a ZOBI on the other end. So that cannot be tested here, right? It's more like an IP level you are verifying.
No, you can. No, because you can have a transactor for the PCIe and a transactor for the Ethernet. You can have a transactor for all of them. Yeah, so you can put multiple transactors onto the onto the emulator, connect it to the SoC running on the emulator, and then put your software running on the emulator as well. And then the simulation environment has multiple UVM environments talking to those transactors. So you could have a PCIe, a USB, an Ethernet transactor all on the emulator, and then you can control the whole emulation through the software simulation by communicating to those transactors.
Yeah. I mean, from this picture, it's not very clear. You might have multiple interfaces.
Yeah, I think this is one just for a block level verification. But that on the right-hand side could easily be an SoC, and you could have multiple transactors.
Just to add one thing. Just to add one thing that it's not only one SCE-MI pipe when you go at the system level. You can have as many SCE-MI pipe, as many transactors you want at the system level. And emulation is the best solution when you do performance testing or when you want to verify SOC. Very plain state. Your question with regard to performance. So I would say whenever you run a test at the system level, and if it takes 2 days on simulation-based environment, on performance, on emulation environment, it will be completed within 6 hours.
Thank you.
Yeah, obviously. That is applicable at in every environment. It's not only emulation, it's simulation or whatever.
But I think the question was, how do you architect your test bench to get maximum performance? Yeah. 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 Because this can often become the bottleneck, which is the thing that slows down your emulation. So you have to architect this right so that you pass. Yeah. It's always waiting for the test bench, and the software is always behind.
Synchronization. Sorry, I'm sorry, but so whenever you talk of synchronization, then DPI-based mechanism is not advised, because I have really experienced like I'm missing data, I'm behind whatever is running in the emulator. So whenever you have to synchronize, DPI mechanism is just to stimulate the things. So the checking mechanism should be on the other side. So means the other side means your UVM side, where you can do in sync all the stuff. Because when you are using C, DPI and UVM and then SCE-MI, so maintaining at the C level, so it's really a challenge. It's really, things become out of sync with regard to the clock and all the stuff which is running on the other side.
So what we experienced, that if it is possible and if it is not too complex to put some of your checkers in the hardware, that would really be beneficial from performance, because let's say your response is coming from your DUT, and over there itself, if you can check scoreboard, then you will not have to pass all that data to the software side.
You're right, but here is a flaw. When you put everything synthesizable, your domain requirement will increase.
Correct. Yeah.
So when your domain requirement will increase, trade-off, then you have to shell off more dollars. You know?
Correct. Correct. Yeah. So trade-off. If you can afford, for instance, then yeah.
Everything is a trade-off in verification. There's a good debate anyway, and maybe after this we can have some food and debate further. But okay, thank you very much. Thanks.